In this tutorial, we're going to be talking about the electromagnetic spectrum and the wave nature of the light. Light actually have a wave character and the particle character. Here we focus on the wave character, and I have a separate tutorial for the particle nature of the light. So before we actually proceed into this section, you must know some of the terminology and some of the terms that we're going to be using in the wave. So let's suppose we have this wave where we have on the x-axis it could be the time or the meters, so meters or the time, and on the y-axis we could have the meters. And the positive sides on the y-axis are going to be, those positive peaks going to be called the crests, okay? And then the negative of those peaks are going to be called the troughs, okay? The distance between the two adjacent crests or two adjacent troughs is going to be actually called the wavelength with the symbol lambda. So I can say the distance from these two crests is going to be your lambda, and the same story, the distance between those two troughs is going to be the lambda. You don't necessarily have to have the definition of the wavelength to be the distance between the crests or the troughs. You could pick any two corresponding points in the wave, and the distance between those two corresponding points is going to be your wavelength. So for example, if I start out with my origin, let's call that 1, and when I go around and follow this wave, the second point where it matches on the x-axis again is going to be 2, but this is not a one full complete wave, it's only half of the wave, and then you go along until you reach to point 3. Now you have completed one full wave, so point 1 and point 3 are going to be your corresponding points in the wave. So the distance between those 2 points, 1 and 3, is also going to be called the wavelength. Okay, so then what if I just randomly pick a point and ask you what's the next corresponding point going to be on the wave here? So let's say I got this point 4. So the next corresponding point on the wave related to the 4 is going to be right here. Let's call that 5. So the distance between 4 and 5 is actually also going to be the wavelength. Okay, so in addition to the wavelength, you must also be able to look at the amplitude of the wave. The amplitude of the wave has a symbol A, and it's just the maximum disturbance along the y-axis. So if I go ahead and change the color here, this is going to be your amplitude. So starting from the x-axis to the maximum height of the crest or even the trough is going to be your amplitude. And then in addition to the wavelength and the amplitude, you also want to be familiar with the speed of the light. The speed of light is actually a constant, and it's going to be c. The symbol is c, and it's going to be 3.0 times 10 to the 8 meters per second. You don't necessarily have to memorize that. That will be given to you for the most part. Okay, now let's talk about what a time period is. The time period is actually going to be the time taken to complete one cycle. So if I start my wave at point 1, how long it's going to take to get to 3, that's going to be simply your time period. And the time period has a symbol uppercase T, and the units we're going to be using to measure the time period is going to be the seconds. All right. More than a time period, the frequency is actually commonly used in case of waves. The symbol of the frequency is going to be a lowercase f, and it's actually just the reciprocal of the time period. It's going to be the number of cycles completed in 1 second, as opposed to the time period was how many cycles, how much time you're going to take to complete one cycle. So make sure you know the relation between the frequency and the time period. The frequency is just the reciprocal. So it's going to be 1 over t. And the units for the frequency is going to be the second inverse, or the other units is called hertz. Then the symbol for that is Hz. Some books may have the symbol for the frequency to be mu, but here we're just going to be using the frequency just to keep things simple. Okay, now in addition to that, we can also relate the wavelength, the speed of light, the time period with one another. So wavelength is actually just the length. So if you go back and recall a simple physics distance, velocity, time formula, the distance is speed times the time. So wavelength here is going to be equal to the speed of light times the time period. So make sure you are aware of this formula as well. And if I want to replace this, if I want to replace the time period with the frequency, this formula becomes wavelength going to be equal to 1 over wavelength, it becomes equal to the speed of light divided by the frequency. So another way of saying the frequency and the wavelength, they are actually reciprocal of one another. They are indirectly related with one another in terms of keeping the speed of light constant there. So if your lambda goes up, which means the wavelength goes up, then your frequency goes down and vice versa. So make sure you are aware of the relation between the wavelength and the frequency. Okay, now let's talk about what happens when the wavelength is actually changed. So let's look at these two waves, and in the green wave and in the blue wave. So know the difference between those two waves. So in the green wave, you can see the wavelength is actually longer, and let's call that 1 here. And the blue wave, the wavelength is actually going to be shorter. So I can say the wavelength lambda 1 is actually bigger or longer than a wavelength 2. So what happens to the energy of the wave when you're altering the wavelength? As the wavelength is increased, the energy is actually decreased. They are inversely related with one another. And if you actually decrease the wavelength, then your energy will be increased. It's an inverse relation between those two. And then I'll have an equation later on. But right now, this is something you need to know. If you change the wavelength, you're actually changing the energy of the wave as well. In addition to that, you also want to be aware if you're looking at the visible spectrum, when you change the wavelength, the color is actually changed, because remember, the colors are associated with the energy. So if you're changing the energy in the visible spectrum, you are going from one color to another color. And you can say the same thing with the wavelength. If you change the wavelength in the visible spectrum, you are going from one color to another color. Okay, in addition to the wavelength, what happens when you actually alters the amplitude? So in those two waves, I can easily see the difference between those two. So this first one clearly have a lower or a smaller amplitude, so we can call that A1. And then in the second wave here, it's going to be A2. So when you change the amplitude, you don't necessarily change the color, but you may change the brightness of the color, you may change the intensity of the color, and you may change the light, the brightness of the light. Um, and if you're talking about a sound wave, then you may change the loudness of the sound. So if I want to look at maybe these two particular waves as in my example, and I know the A2 is bigger than A1, so I can say the sound of wave 2, so sound coming from a wave 2 that has amplitude A2 is going to be bigger than the sound that's coming from a wave that has an amplitude A1 here. So when we are looking at the colors, I can say their intensity of the color is going to change, and you don't necessarily change the color when you are changing the amplitudes. Okay, so make sure you are aware of the difference between the wavelengths and the amplitude changes. Let's talk briefly about the electromagnetic spectrum. I'm not going to spend too much time on it. I'm just going to be briefly mentioning about all the radiations you have in the electromagnetic spectrum. So the electromagnetic spectrum actually starts with the gamma rays, followed by the X-rays, and then you have the UV, and then you got this little section of visible spectrum. So the visible spectrum in the whole electromagnetic spectrum is actually very small. And then you got these IRs, the microwaves. The radio waves is relatively a big section in the electromagnetic spectrum. And if I talk about their energies, the frequencies, and the wavelength, I have written down here. So on the left side, you have high frequency and the energy. So the gamma rays have very high frequency, and they are actually very energetic. They are the most dangerous radiations we have in the electromagnetic spectrum. And then as they're moving along, their energy and the frequency is actually decreasing, and by the time you get to the radio waves, their energy is actually very, very small. Okay. In addition to that, you want to be aware of how the wavelength is changing when you're going from the gamma rays to the radio waves. The gamma rays actually have a shorter wavelength. So I have made this picture on the top where you can clearly see how the wavelength is going to be changing when you're going from the left to the right. So obviously the wavelength has gone a lot bigger from left to right. Um, you want to be aware of where those radiations are with respect to one another. You don't necessarily have to know the numbers of the frequencies and the wavelengths. Like for example, you want to make sure you know the X-rays are have low energy than the gamma rays, but they are high energy than the UVs. Okay. We all aware gamma rays sometimes are used in radiation therapy because they're so energetic they can be used to kill cancer cells. X-rays we are all aware of. They can't pass through a very dense medium, and they are used to take the structure of the bones. Gamma rays can't be used for that because gamma rays are so energetic they even penetrate a very dense medium. To protect yourself from the gamma rays, you must use a very solid lead jacket or maybe a very thick concrete wall. And we are all familiar with the UV rays. We have the ozone layer that protect us from the UVs. The UV rays are used for tanning purposes as well. And then we have this little section that's visible spectrum. So I'll come back to that in a minute. And then we got these IRs. So the IRs actually used in organic chemistry a lot, and then IR rays are also detected by some animals. The microwaves are actually used in the actual microwaves in the kitchens. And if you wonder how the microwave really works, the microwaves actually have enough energy to excite the water molecules bond. So if you have a food that does not have water in there, it will not warm up in the microwave. So if you want to test that, go ahead and test that. But every single food that's out there has some sort of water in there. Like you don't necessarily see the water, but it has the moisture in there, like bread or we can talk about tortillas. They all have the moisture in there. And then obviously the radio waves is a big section in the electromagnetic spectrum, and it's obviously used in cell phones, the FM radio station, the AM radio station. They all use radio waves, and also um, the tower signals, the airplane signals, or the missiles. They all use the radio waves for that. So their radio waves are actually the longest wavelength, and they the in terms of how small and how big the wavelength can be for the radio waves, the smallest radio waves are about 1 millimeters, but then the longest radio waves could be as long as 100 kilometers. So they are actually they have very long wavelengths, and they are the lowest in energy out of all the radiations in the electromagnetic spectrum. Okay, so let's go back and focus a little bit on the visible spectrum. So in the visible spectrum, we have obviously this rainbow, 7 colors, and if you want to memorize what the order of the 7 colors are, just memorize this this word. It's called Vibgor. So it stands for the violet, indigo, blue, green, yellow, orange, and red. So this is how the order gonna be, and you don't have to know like what particular color correspond to what wavelength. You just it's a good idea to know the range of the visible spectrum. It goes about 400 to 700, and you want to know which color has longer wavelengths and which colors have the higher frequencies and stuff like that. So for example, out of all the colors, the red is going to have the longest wavelength because it's far on to the right side, and then out of all the colors, the violet probably going to have the highest frequency or the highest energy because it's on more onto the left side. So as you go to the right side, your wavelength is increasing, and on the right side, on the left side, you're gonna be having a higher frequency and a higher energy. So make sure you know the energy and the wavelength differences among the colors, not necessarily memorize the numbers. Okay, so let's look at this question real quick here and see what we just learned so far, all these formulas, if we can apply it to this particular question. So the question is asking, calculate the frequency of the blue light that has this wavelength. So for the most part, the wavelength is going to be measured in nanometers. All right, so you may want to pause the session here and figure out the answer of this question and see if it matches with yours. And before we do anything, we want to make sure we get rid of the nano there. And nano is one of the smallest prefixes we got out there. And if you recall, the nano is 10 to the minus 9, so that's how much wavelength we have in there. And if we're trying to figure out the frequency, recall this formula where the wavelength is actually going to be equal to the speed of light over the frequency. So I know my wavelength, my speed of light is going to be 3.0 times 10 to the 8 meters per second. So I know my speed of light as well, and it should be easy to figure out what the frequency is going to be. So if I rearrange this equation, and I can multiply both sides by the frequency, all right, and I can divide both sides by the wavelength. So when I do so, your new equation or the manipulated equation becomes frequency equals to speed of light over the wavelength. Now all I really got to do is just plug in those numbers in there. So your speed of light is 3.0 times 10 to the 8 meters per second, and your wavelength is going to be 470 times 10 to the minus 9 meters. Okay, so your meters will cancel out, and your frequency is going to be in seconds inverse, or also you can say in hertz. So let's see what that comes out to be. So I have 3 times 10 to the power 8, and divide that by 470 times 10 to the power negative 9. All right, so after plugging this into the calculator, I get 6.38 times 10 to the power 14 hertz. So that's going to be the frequency associated with this blue color. Okay, so like I said, light can have the wave-like phenomena and the particle-like phenomena. So some of the wave terms that we just talked about and some of the phenomena of the light that treat the light as a wave are going to be interference, the diffractions, the reflection, and the refractions. But we're not going to be talking about all of those. I just want to briefly mention about the interference because it's something that you guys will see in an everyday life. So interference is just summing up the two waves, and you can sum up the two waves or more than two waves two different ways. And one way of putting or adding the two waves together is called a constructive interference, where when you're trying to amplify things, like if you have, one speaker that doesn't really give you much sound, then you put another speaker in phase, and that amplifies the sound. So in that case, you have two or more than two waves are added in phase. So what does in phase really mean? So when we look at this example right there, I can say I have this like an orange wave and the green wave here. So the crest of this orange wave and the crest of this green wave, they matches with one another, and I can say the trough of the green wave and the trough of the orange wave, they matches with one another. So these two waves are added in phase. So when they are added in phase, you get a constructive interference where your amplitude is going to be the sum of the two other amplitudes. So let's say if I want to figure out what this amplitude is going to be, then I would have an A1 here and I would have an A2 here coming from those two waves. So my resulting amplitude is going to be the sum of A1 plus A2. So that's called a constructive interference. And then in addition to that, you can also have the destructive interference when the two or more than two waves are actually meeting out of phase. So if I look at this example here, I can see my orange wave here and my green wave here. Their troughs, their crests are not matching with one another anymore, but instead the crest of this orange or yellow wave is actually overlapping with the trough of the green wave. So they are meeting out of phase. So when they meet out of phase, you actually subtract their amplitudes. So the resulting amplitude of this final wave, when you add those two together, is going to be A1 minus A2. And it seems like here the A1 and A2 are exactly equal to one another, and that's why you really don't see any wave here. All your amplitude has been canceled out. Um, where do you really use the destructive interference? Well, those really expensive headphones, they can they use this phenomena of destructive interference. So what they do, they cancel the noise by creating by creating the sound waves that meet with the external noise in terms of destructive interference, so that you can cancel the most of the noise that's coming from outside. Okay, so that's a typical example of the wave-like character of the light, and obviously, there are other phenomena that light exhibit that tells it's going to be behaving like in a wave. But we're not going to be talking about those. If you take physics course, that's when you learn more about diffraction, reflection, and refraction. Okay, so hopefully this video was helpful, and I have another video posted that describes the particle nature, how you're going to be calculating the energy and the photoelectric effect of the light. If you have any questions, please leave the comments.